Welcome back. In this segment, we will describe an algorithm to solve a whole class of recurrence relations called LHRRCCs that we defined in the previous segment. Now, every LHRRCC must be defined in the following way. A sub n, which is the generic term, must be defined as the sum of the previous terms multiplied by coefficients. These terms must be added together, not multiplied together. Notice if the coefficient is negative, then it's the same as subtracting this term. The terms cannot be squares or third powers. They must be linear terms. That's the case here. And there can be any extra components here on the right. So this is a homogeneous recurrence relation. Now notice that in our notation, the previous terms are listed from n-1 down to n-2 down all the way to n-k. So n-k is the smallest of the previous terms that is used in the definition of A sub n. Now it turns out that there is a different way of writing this definition which is equivalent, but that will prove useful to us in the algorithm. So let me introduce it right away. So here what we're going to do is pretty simple. We're just going to move all of these terms to the other side of the equality. So when we do that, we get A sub n minus all of these terms, and that sum is equal to 0. The advantage of this formulation is that it looks like an equation, and this equation is going to be very important in our algorithm. But first, let me make a couple comments. The first one is that some of these coefficients might be equal to 0, which means that some of these terms might disappear. You're not required to have all of the terms from A sub n minus 1 down to A sub n minus k as we saw in previous examples. However, there must be some term that has a non-zero coefficient, and that has the smallest index of the term here, this A sub n minus k. And this particular k has a special meaning, and we give it a name. It's called the order of the recurrence relation. So the order of the recurrence relation is k if and only if c sub k is the last non-zero coefficient. What do I mean by the last? Well, I mean, remember we ordered the coefficients and the terms in decreasing order of the index of the previous term. So A sub n minus 1 is the term just before A sub n minus 2 is the term 2 steps back, and A sub n minus k is the term k steps back. So the order of a recurrence relation, the integer k, is basically the smallest term before A sub n that A sub n depends on. So how far back do you have to go to get the smallest term in the definition of A sub n? That's what the order is. And the second definition then is to give a name to this equation. This equation is called the characteristic equation of the LHRRCC. However, it must be modified in a certain way. So the characteristic equation is not exactly this equation, but it's obtained from this equation. So let me write it down again, and let me explain how we modify this equation to get the characteristic equation of the LHRRCC. Well, the first thing we're going to do is we want to replace these a terms by a variable to make it into a real equation. So we're going to do that one by one. Let's call the variable of this equation x. So we've replaced this a by an x, and then this a by an x, and then every single a is replaced by the same variable, say x. And then what we're going to do is we're going to replace each occurrence of n here by k. And in the process, we're going to move the subscript to a superscript. Because remember, in an equation, in a polynomial equation, we have x to the power something. The superscript doesn't mean anything in arithmetic. So again, I'm going to replace this n with k, where k is the order of the recurrence relation. And I'm going to move the k to the power. So this becomes x to the power k. Now this n is going to become k. So we got k minus 1. We move it up to the power of x. Same thing for this n. We place it with a k. And all the way down to the last term. Now let's be careful here. Notice what happens is when you go from left to right, the power of x decreases from k to k minus 1 to k minus 2. So here what happens when we replace the n with a k? Well, we get k minus k, that is 0. And of course, x power 0 is 1. So the last power of the variable x is just 1. So we can remove it. And let's tidy up the equation by moving everything closer together. And this is what we call the characteristic equation of the LHRRC. So to summarize the process, if you start with a LHRRC, you first rewrite it as an equation like this. Then you replace every term by a variable, the same variable x. And then you replace every occurrence of n in the index of the terms by k. And you get the so-called characteristic equation of the LHRRC. Now that these preliminaries are out of the way, we're ready to describe the algorithm to solve the class of recurrence relations called LHRRCs. So let's say you have a LHRRC to solve. The first step is to build its characteristic equation as we just described. The second step is to solve that equation. Now notice this is a polynomial of degree k. You should remember that this type of equations have exactly k solutions, which means the polynomial here has exactly k roots. So you find those by solving for x in the equation, and what you get are the roots r1, r2, dot, 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 rk. These are just real numbers that you have to determine. Now the third and last step is to use these roots to find a solution to the recurrence relation. Now first there's a condition in the last step. These roots must be distinct, otherwise the algorithm doesn't apply. So let me give you an example where this algorithm doesn't apply. Let's say you have to solve this characteristic equation, which is a polynomial of degree 2. So you know there are two roots to this polynomial, or two solutions to this equation. And of course you recognize this as x plus 1 squared. In other words, this equation. And then you can tell that the first root is minus 1 and the second root is also minus 1. So this is a case where the two roots of this quadratic equation are not distinct, and that's a case you don't want to consider for this algorithm. Now if it turns out that the roots are distinct, here is how you build the solution to this recurrence relation. The solution is a definition of a sub n that is not recursive. Of course it depends on n, but it's a closed form formula that allows you to plug in the value of n and get the value of a sub n directly. And here is the form of this solution. The first thing you notice is you have all the roots raised to the power n. So this is where the n comes in. So you have the nth power of r1, the nth power of r2, and the nth power of rk. And you add all of these terms together after multiplying them by some coefficients, alpha 1, alpha 2, and alpha k. So again, everything here is a constant, a real number, except the n. So this is a closed form formula for a sub n for n equals 0, 1, 2, and up. And let me remind you that these alpha 1, alpha 2, dot, 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 alpha k are just real numbers, just constants. And this is it. This is the algorithm that, starting with any LHRRC of this form, gives you its generic solution like this. I will describe and trace this algorithm on an example in the next segment.